Hello, everyone, and thank you for listening today to episode 670 of People Behind the Science. We're looking forward to revisiting our interview with Dr. Lee Cronin, originally released on July 15th of 2015. Listeners, Lee is a distinguished chemist who leads one of the largest multidisciplinary chemistry-based research teams in the world. They work on a variety of questions, including those related to the origins of life, creating artificial life forms, discovering alien life forms, digitizing chemistry, understanding how information can be encoded into chemicals, and developing chemical computers. And in our interview, Lee shares more about his life and his research. So I hope you're ready for this episode of People Behind the Science.
Every day, discoveries are made that will change our understanding of the world around us. Dr. Marie McNeely is here to bring you the brilliant minds who are making these discoveries so they can share their incredible stories and take you on an amazing journey. Welcome to People Behind the Science.
Hello, everyone, and welcome to another episode of People Behind the Science. I am thrilled to have with me today Dr. Lee Cronin. So Lee, welcome to our show today. How are you?
Very well, thank you.
Wonderful to hear. Well, I'm excited to introduce you to our listeners, Lee. So listeners, Lee is the Regius Professor of Chemistry at the University of Glasgow. He received his bachelor's in pure chemistry with first-class honors, as well as his PhD in organic chemistry from York University. Afterward, he served as a research fellow at the University of Edinburgh, an Alexander von Humboldt Research Fellow, and a lecturer at the University of Birmingham, before joining the faculty at Glasgow University, where he is today. Now, listeners, Lee is an accomplished chemist and has been honored with many awards, including recognition as one of the United Kingdom's top 10 inspiring scientists and engineers by the Engineering and Physical Sciences Research Council in 2014. He's also been listed as one of the top 100 United Kingdom practicing scientists by the UK Science Council. In addition, he received the Royal Society of Chemistry's Corday Morgan Medal and Prize in 2012, and he is a member of the Royal Society of Edinburgh and recipient of the Royal Society's 2013 BP Hutton Prize for Energy Innovation for Applied Research, as well as the 2015 R.S. Tilden Prize for Pure Research. Now, listeners, Lee is here with us today to share his journey through life and science. Now, Lee, we want to get to know you today and your science, so can you start by telling us what you like to do when you're not doing science?
Well, I guess the thing I do a lot, which I've done since I was probably about 5 years old, is taking things apart, like anything. Calculators, TVs, cookers, anything I could get my hands on.
Are you good at putting them back together then?
When I was younger, I could never put anything back together. As I've got a bit older, and my kids kind of demand so that they can share the fascination for seeing the innards of the object, they demand it to work afterwards. And I must say that I have a pretty bad track record, but it's getting a little bit better.
Gotcha. Well, I think I was the same way as a kid. I was always taking things apart and then just kind of leaving them there for someone else to clean up.
So increasingly, we do got a 3D printer at home and some electronic working, and I have some drones and we try and program. And so I tend to play with technology a lot with my kids if I'm not running or trying to find time to do some reading.
Fantastic. Well, great to get a picture of your life outside of science. You mentioned you like to read, and I always love to get book recommendations from the people we have on our program. So I'm going to ask you for a recommendation today, and this can be a science book or a non-science book.
I'll tell you what, I'm reading a collection of short stories called Mortal Engines by Stanislav Lem. Stanislav Lem wrote Solaris.
Gotcha.
And he's one of my favorite science fiction writers because he wrote about artificial intelligence and robots and things, and I just find it fascinating. But my classic book that I love the most, that changed the way I thought about the world, I suppose, is a bit boring. It's Zen and the Art of Motorcycle Maintenance.
Really? Why that book in particular?
It was a really interesting philosophy about kind of trying to meditate in your reality, to try and understand how your reality works and focus on processes. It's a bit like writing a nice piece of music or fixing a job properly, like fixing a tap or getting your car to work. I don't know. It's just this whole idea about understanding the system outcome, not just doing one bit well.
Well, fantastic recommendations. I'll definitely put those out on our website if our listeners are in search of their next book. And great to hear about your life outside of science, Lee. But next, I want to dive into your science. So can you tell us how you describe what you do to someone who might not be familiar with your work?
As I feel not so familiar with my work sometimes, I try and explain that I'm a researcher. The thing I try to do mostly is ask questions in a really odd way. But I'm really interested obviously in chemistry, molecules, and I suppose, depending on who's asking me the question, I will try and give it some kind of application context. Obviously, from a fundamental point of view, I'm interested in how life got started, but more pertinently, how I can make new life forms from scratch. Now, that's a pretty big discussion to have from the word go, but sometimes I frame it like I'm interested in discovering new antibiotics or making molecular machines. It very much depends on, because we do so many things, obviously it's all about manipulating chemicals and understanding chemistry, but there's just so many different avenues you can go down. I can normally make it fascinating for the person. A lot of people think that chemistry is dirty and boring. Far from it.
Gotcha. Well, I think that is a wonderful description. I like how you're really diving deep in both the pure and applied worlds in chemistry. And we'll talk more about your work as we go through the interview. But next, I want to hear about what motivates you. I think there's so much to get done in a day as a scientist that it kind of helps to have these little motivational quotes or inspirational quotes in your head as you go through. So do you have a favorite?
Not really. I suppose I have a few mentors that give me the odd quote now and then. And there's an Noel Howard quote, I think, that was basically, it doesn't matter how many times you get defeated or rejected, you just have to keep going. And there's also a Winston Churchill quote along those lines. But in terms of motivations in general, I just like to remind myself that I'm motivated by the question. And I suppose that's it. So maybe I could inadequately paraphrase some of Richard Feynman's quotes, but it's just this idea of being fascinated by the question, why? Why does it work? And when people don't understand your science, or they reject your proposal, or reject your paper, or just reject your whole viewpoint, I take a lot of comfort from the fact that I am interested in my lack of understanding. And I think that that concept has really liberated me a lot, because it stops you from worrying about whether you're smart enough to do it. You start to figure out if you're inquisitive enough to do it.
I like that. I love the emphasis on curiosity rather than some sort of innate intelligence. I mean, you need to have some aspect of problem solving and critical thinking, things like that, to be successful in science. But I think the curiosity really drives it. So fantastic to hear about what motivates you. And you mentioned you've had some mentors along the way who've inspired you, perhaps, with these little quotes and sayings. Can you tell us about some of these role models you've had?
Yeah, I mean, there's one particular role model. He's a good friend, actually. He's a Scottish academic, but he left Scotland and went to England, and then left England and went to the United States. And actually, he got knighted a few years ago, so he's a Sir, but I think he's also an American citizen, but I think he's done a deal so he can keep his knighthood. But as an older scientist who's very famous and very good at what he does, he's seen it all and done it all, and it's often good to talk to say, am I on the right track here? And I feel a bit defeated, and he's very comforting to hear that he has the same problems. It doesn't matter how good you are at your science, how many Nobel Prizes you may have, you'll still get things rejected. And I think what we've got to try and do is explain to people that rejection in science is actually a good thing. It's not like you were rejected by your family or something.
Right.
It's actually an essential process, and it's about clarification and also sharpening your knife of reason, if you like, or your pencil, to actually explain to people why you're doing it's important and why they should be interested in it, because there's only so much bandwidth that we have.
Absolutely. And I think it helps in science that usually the rejections don't just come as a flat rejection. They usually come with a lot of constructive criticism to help you out along the way.
One of my other mentors is a professor in Manchester. I just published a paper that he really liked, and I really look up to him because he's a very detailed person, and he would always tell me if I needed to apply more detail to a particular problem. And he came up to me and said, I don't know how you do it. You seem to be able to do this great science, but you don't know anything. I actually took that as a compliment.
Sure.
Because I'm motivated by the problem, not by the expertise I have to solve the problem.
Gotcha. Well, I think that is fantastic to have these mentors along the way. And I love hearing stories about the people who've inspired scientists along the way. But I'm curious now to take us back to the beginning, Lee. Can you tell me how your interest in science began and what set you on this path initially?
I don't know. My view changes. My recollections change over time. But I remember as a child just being fascinated by the world around me, what I found. I was always very curious, taking things apart. I was always also interested in minimality. I had an obsession when I was about 5 years old of building pocket survival kits. How could I recreate my reality with the minimum stuff in a matchbox? Could I have clean water, some kind of way of starting fires, some way of trapping food? So I was interested in how I could get maximum information into minimum stuff and then use that minimum stuff to recreate my entire reality. And this kind of probably has some reflection now why I'm trying to understand how life came from nothing.
Interesting. So then did you ever have to use these survival kits, or were you maybe in the Scouts or anything like that?
Yeah, was in the Scouts and in the Air Training Corps and so on, and of course we use the techniques, but no, I mean, I've been wonderfully pampered by society. I think I remember going to the chemist and convinced them giving me some Corday crystals, which is potassium permanganate, and you add a crystal to a litre of water and it goes purple and you can drink it because it's then all the bacteria have been oxidized and whatnot. Mm-hmm. The manganate is probably more toxic than the bacteria.
Gotcha.
Drinking this pink water thinking it wasn't tasting very yummy, but anyway, that was a long time ago.
Gotcha. Well, wonderful to hear about how this problem-solving nature was developing in you, even as a kid. But now, can you tell us how you went from this sort of minimalistic, trying to get all the answers into a small box kind of kid to where you are today? What are some of these key moments along your path that really helped you get there?
I just had a very tricky time at school for reasons that are too boring to go into, because everyone has their own little story. But to truncate it slightly, I was basically in the learning difficulties group or stream there.
Really?
It was fascinating because basically no one had any expectation. And so because I like daydreaming and doing maths in my own time and looking at combi theory and so on and physics, when I was in the primary school, I was basically allowed to do whatever I wanted. So there was no expectation until toward the end they figured out they didn't think that I could read or write because I refused to demonstrate to them the ability to read or write, which caused a bigger problem because when I went to high school, I was subsequently also put in the learning difficulties group. But again, although that was potentially disastrous from having a nice path through school and getting to university, people have no expectation of me, so I could learn what I wanted to learn.
Sound like you gamed the system, Lee.
It didn't feel quite that way. It was quite distressing because I realised I loved science and maths. Actually, I did like English and I still like English, but everyone thought I couldn't do it. So it was kind of a bit crazy situation trying to convince them that I needed to go on to the sixth form just before university so I could get to university because I really wanted to go and do physics or chemistry at university. So that was a small error.
Gotcha. So how did you convince them?
Long story short, because of the way the courses were run, it was physically impossible for me to actually pass some of the courses at the top grade. But we convinced the teachers to enter me in, even though I hadn't done any of the coursework or done any of the syllabus, and I passed.
They were willing to let you give it a try then. I like it. So Lee, then what happened next? So you went to university, and how did that interest in chemistry develop?
I had a very good chemistry teacher, basically. I was split on whether I was going to do physics or maths. I started computer programming when I was 9, when I got given the ZX81. So I was playing around in assembly, which was kind of cool, like you do back then. So I kind of didn't want to do computing at university because I felt that I was already quite good at manipulating, playing with computers and writing code. Well, I suppose I was not very good at chemistry, and that motivated me to try and understand why I wasn't very good at chemistry or why I found it so confusing. And so that coupled with a very good teacher and the realization that chemistry is so important and so interesting, there are many questions, I was just hooked. And there was a great university that was recommended, and that's how I found myself going to York University.
Very interesting. And I know a lot of people out there are in a position when they're maybe starting undergraduate and they are struggling with chemistry. So what advice can you give them for how to get through it? I know I myself was in the same position and ended up kind of directing my interests in science in a different direction. Well,
you see, the thing is, because I never had the burden at school of having to learn anything, just derive everything from first principles. And that's what I did. That's how I got through my school exams, because I hadn't read the syllabus. I didn't know what it was. I just had to go on what had interested me. So similarly, I applied that kind of tactic when I was doing my undergraduate studies, and I felt I could really get into, at a deep level, the chemistry and really confront what confused me, which was pretty much everything, from thermodynamics to inorganic chemistry to organic chemistry to all the different issues and quantum mechanics. And I just really enjoyed being confused. And I got a good network of friends who were very, very smart, much smarter than I am, and they were able to teach me in the pub. And I realised that I had a passion for asking the questions and going about it. And I suppose that's how I stayed turned on to chemistry, because I was really interested by the bits that confused me. I think the problem is nowadays that people are very formulaic, so they just want to know the answer. Mm-hmm. In chemistry, there are a huge number of facts you need to know, but you don't actually have to memorize them. And there is beauty in chemistry, the way there's beauty in mathematics and the periodic table and physics. The beauty is there, the questions are there. I think the problems need to be presented in the right way. Understanding the chemistry of what goes on in a stem cell to make it decide to become a brain cell or a kidney cell. Isn't it fascinating that actually the code for that, or the state space, has been decided by evolution, so that stem cell could equally become those cells, and we have no idea how that works.
Absolutely. Well, wonderful to hear about your experiences, and reassuring, I think, for a lot of us to hear that now a successful chemist did struggle in the beginning as well, that it wasn't something that just came naturally to you. And I think that's the case for a lot of scientists. It didn't necessarily come naturally. It wasn't something where they knew everything going in and had everything figured out. So wonderful to hear that. And I'm curious to hear now, you traveled a little bit sort of between different institutions after graduating with your PhD. What then allowed you to settle at Glasgow? Was there a particular attraction for this area, wanting to get back close to home, or what brought you there?
My Scottish wife.
Oh, yeah?
Again, a combination of circumstance that's a bit complicated to go into, but I wanted to stay in the UK. I've been abroad, so in Germany before going to Birmingham, and then I wanted to stay in the UK because I figured it was a very good place for young people to get research started. And obviously when you're young, getting your first faculty position, trying to get money to convince people that you can do science, then actually doing something interesting, I mean, it's probably one of the hardest jobs you can think of because you have to do everything. So my family were very supportive, and my wife got a really good job at a pharmaceutical company up here, and it just worked out really well. And Glasgow, as a university, is really interesting because it's an old university, almost 600 years, but it's a civic university because it's a big city, and it has to cater for all sorts of students from all sorts of walks of life. And the thing that I love so much about this place is that you've got so many different disciplines. Just 100 metres from my door, there's a great physicist down the corridor that I collaborate with who actually is decreasing the speed limit for light and increasing. There's all sorts of crazy things he's up to.
Oh, wow.
There are people in engineering that can make me nanoelectrodes so I can put my molecules in to make molecular memory. There are people in biology which are interested in helping me make sensors to detect whether you've got an antibiotic resistance problem or a virus problem. So there's loads of people nearby that are really smart that you can access, and I think although Glasgow is a large university, it's got a really interesting interdisciplinary feel about it.
Wonderful to hear. So tell us a little bit about what you're working on at Glasgow. What is this project that you have going on in your lab right now that you are just the most excited about?
The thing is, I have quite a number of projects in my lab, and it's like ask me to choose my favourite child. I can't do that. They're all fascinating, but I think I'll tell you about two that are related and you can kind of get together. I like to annoy people in science, and I don't mean annoy them by challenging their political beliefs or...
You're not the front row heckler at a talk, yeah.
But I want to annoy them in terms of saying, well, why do you think like that? And of course, it can be annoying because it's quite clear why they think like that, and there's hundreds, if not thousands of years of precedent, but occasionally I just like to ask them why and to challenge their axioms in a new way. And so a few years ago, well, in fact, my entire academic life, I've been obsessed with one problem, which is, how does chemistry get complicated? Now, that's kind of like a really simple question. How does chemistry get complicated, and why should you care? Well, complicated chemistry gives rise to biology. Now, how does chemistry get complicated? Well, you have to fuse atoms in stars and explode them and produce heavy elements. So chemistry is really trapped in the middle between sexy Big Bang physics and sexy biology. But chemistry is actually on a path, on a journey towards the complexification of our universe from simple elements to... So I just wanted to ask where they came from. Now, that's very taboo in some respects because people think that this is a history experiment, that you have to think about plausibility, conjecture. And I thought, well, actually, I want to get rid of that. Let's pretend that life is easy, that going from chemistry, inorganic sand, to biology is just easy, and you just need a bit of time, a bit of jiggery-pokery.
It's a technical term right there.
And if you do the right operations, out will come a life form. Now, when you say that, everyone says, nonsense. It takes hundreds of millions of years to make the soup. Then there needs to be molecular evolution. Then there needs to be this, that, and the other. And actually, all these assumptions that are made are not necessarily required. So what we're trying to do in my lab right now is basically make a chemical search engine, a chemical Google, that will actually search through chemical space to look for the processes that could give rise to biology. So that's what we call bottom-up life, from the bottom, from sand to biology. The other thing we're doing in my lab is we're going from technology to complicated chemistry. So we want to see how we can get chemistry complicated by programming it. Now, if you lie these problems up side by side, you can see they're in fact the same problem. It's all on how do you take random stuff and turn it into biology, and how can you deconstruct biology and understand how to discover new drugs. And so what we're doing in my research group at the moment is we have a gargantuan effort of many, many, many tens of people that are working on this project, are all working on different aspects and linking up. We're making robots, we're doing organic chemistry, we're doing biology, we're doing new electrical engineering, we're writing software, we're writing data analysis, and all this team is a bit like a large hadron collider for the origin of life, but more importantly, I call it artificial life. We're trying to work towards making a completely new artificial life form.
Very, very interesting. Now, I understand over the years you've also gotten into some of the applications of 3D printing, and this is something that I am just absolutely fascinated in, all the possible directions that 3D printing can take us. So can you tell us about your work in that area?
The reason I got into 3D printing was not because of all the kind of wow with the look, we can print a three-dimensional plastic object.
You cannot deny the wow factor, though.
Maybe.
Perhaps.
No, I like it. But what it does is a 3D printer gives us something very, very nice. It gives us a very cheap robot. If you think about it, the reason I got into 3D printing was not to 3D print plastic and do chemistry just that way, but was to actually rehack the 3D printer into a chemist, or to be a very fast chemist so we can start making the engines for the origin of life and also turn them into drug discovery engines. But then I realized, 3D printing is cool because you can print prosthetics. You can print functional membranes. You can do all sorts of interesting little things. So I then got thinking about what chemistries could we do to enhance the 3D printing process and also to make it more applicable. So we're having a lot of fun. It raises a few eyebrows because it's certainly not pure science. It's not even really university level engineering sometimes because it is so hackable and accessible. And I think that's one of the really nice things. If I could use a 3D printer, turn it into a kind of chemistry set, if you like, or a programmable digital chemistry set, I can maybe use this with my research group, maybe as outreach in schools that you can do programming, electronics and chemistry all at the same time. That would be awesome.
Absolutely. And I think thinking back on my graduate and undergraduate school experiences, a lot of the lab pieces of it, and maybe some of the even basic research, you just spent a lot of time pipetting. And this is something that, you're right, the 3D printer as a robot could almost do for you. So do you foresee this being something where you're almost replacing some of the lower level functions within the laboratory with these 3D printers? Or is this something you're doing now?
And I wouldn't just say lower level function, I would say kind of things we take for granted. There is some really interesting maths in this, actually, but it's all a bit about how you do experiment and actually move through the operation, what I call operation space. You would call it low-level pipetting. I would call it operation space.
Sounds a little fancier that way, yeah.
It's like how you combine. Do you add A to B or B to A? Or do you put them together at the same time? Little things like that. Those little bits allow you to basically go pro with your experiment. And what I mean is literally strap a webcam to your shoulder and video yourself doing the experiment. You could do that, or you could tell a robot how to do it, and the robot knows what it's done, you know what it's done because you've told it. So it's not about replacing the person, it's about enabling the person to know what they've done and very quickly plan the next experiments. And on my website, I've actually got a link to a couple of open access papers where the 3D printer is used as a pipette and you can see it to make quirky droplets that literally have a life of their own.
Well, phenomenal to hear more about your work and some of the big, exciting experiments you have going on in the lab. And I know we've made your adventure in science so far sound relatively easy. And I know that's not the case for a lot of people. I know there's a lot of struggles, a lot of challenges along the way. So can you take a moment to think back on your whole journey and tell us what was one of the most challenging times for you, or one of these biggest failures, quote unquote, that you think you've had?
Oh, I think I'm having it right now this week, actually.
Really? I've caught you at a great time then.
Particularly bad day. We've been going into a new field of chemistry that is very well established. It's 100 years old. And we have discovered a series of new phenomena. And try as we might, we can't convince people. Well, actually, I go to the world and I pick a person at random who's an expert in the field, let's say. And I tell them about my discovery. And there's one of two responses I get. First is, dismissive. That's obvious.
All right.
I'm kind of crestfallen. I go, why? And they explain. I'm like, okay. And then I go to the next person, tell them about it, and they say, that's impossible. that can't work. All the people I've talked to about this fall into these camps, these binary camps.
Really?
So this paper has been rejected. The proposals are rejected. My researchers who are working on it are dejected. I am frustrated. But you know what? The thing that really makes it really interesting is that there is something there that doesn't sit. And when you've got two communities telling you the opposite and being so certain in their dismissiveness of you, you know you're onto something. And it's nice because I have a big research group and we have some projects that are easier because we are in our dogma or the field is accepting of us, we are there. And there are new fields that what I like to try and do is have things that are succeeding and failing at the same time, because then you can see the whole picture. You can reassure your students.
Sure. Evens it out a little. Yeah.
You know, this is a 5-year project. I've spent money that I don't have on it. If the bailiffs come, I'm so fired. I've taken a huge risk on this. So I should be terrified and having a nervous breakdown. But actually, I'm quite enjoying... It's not a fight. I mean, people are not trying to be nasty. They just don't get it. And so that's part of my job, I think, is to basically do things that I don't get and they don't get. And some of it's going to be nonsense, and some of it's going to be not nonsense. And I guess I'm a bit distraught because I can't work out if it's nonsense or not. I'm normally quicker at working it out, and I don't think it is. But the longer you take and the more money you spend, the more people's careers that you invest in this, the more risky it becomes.
Sure. So can you reveal in a few sentences what this project is related to?
It's to do with the origin of life, and it's to do with making proteins. I could say that.
Gotcha.
But because it's not published yet, I fear that it probably wouldn't be fair on my co-workers or actually the field, because, you know what, I could be wrong. As one of the editors I was talking to, who nicely put it, said, you know what, Lee, you're convincing, but you could just be wrong.
And this is possible.
And this is possible. So it's not that peer review is the be-all and end-all. It's a comfort blanket. Peer review is a comfort blanket. If you can get your paper published through some pretty stern criticism and turn them around, which I think is the most fascinating outcome, then you know that you're making good arguments. I think it's easy to dismiss peer review and say no one gets it because they're idiots or whatever. I think that's not fair. The system is the system. It's built upon human beings who understand, who are experts in their field, and they understand where it is. And it's my job. The burden of proof is on me. I take that. I'm used to that, but it's pretty hard. And when it starts to all go wrong at once, you can go through times where everybody just tells you everything is wrong. Mm-hmm. And so you just have to find the motivation from somewhere. And I think what motivates me, what gets me through it, is I'm just so interested in what's going on. What we've found is so interesting. And when you do find people with their guard down, they say, oh, can you do this experiment, that experiment, and that experiment? And before you know it, you can see there's an entirely new field. This is what keeps me going, is providing the energy. And I think I've convinced my poor student, who's like, am I going to get a PhD? Are you sure? Oh, it's okay, relax. You don't just have to publish to get PhDs, or he will. I mean, it's just would be unheard of that he wouldn't. But it's hard, and failing is not easy.
Absolutely.
Well, actually, it's easy for me. I'm really good at it.
I think a lot of people struggle with it, though. I think it is a skill that you have to learn as a scientist to fail and then be able to bounce back from it. So there are those projects, though, that I've heard science talk about that you have to draw the line at some point and decide when you're going to quit. Have you drawn a line for this project yet, or are you still giving it a chance?
I'm not quitting because it works. Mm-hmm. So when we started the experiment, and I said to my colleagues, is it going to work? They all said, no, it's not going to work. And they were being friendly about it. And then we got it to work, and they went, it's obvious. And the other half went, it's boring. It was kind of interesting. So I guess, do you draw a line under it because all we want to do is say everything we do is novel? Well, I don't understand reality. Reality is telling me something new. And as long as I can convince myself that the data that we're collecting is robust and the experiments are reproducible, then when we do our interpretation, that's the bit that we then start to discuss and convert people on. But yeah, there are some things. I mean, I've made discoveries in the past where I thought I'd made a room temperature organic magnet. And it was too good to be true. Mm-hmm. And it worked, it was brilliant. I was getting ready to write the paper, and then I just said, this is something wrong here. So I split my group into two and said, right, go away and reproduce each other's work. And you know what? They couldn't do it. And I was so devastated. I then asked my friend in the USA to do it, and he couldn't do it. And then a few days later, he could do it, and then he couldn't do it. And then we realized that it was an impurity. And I'm very proud of myself for that, because we never even wrote the paper. We never even started. We thought about it, and we just drew a line under it and said, we've made a mistake. It's not what we think it is. It's an impurity, and this is the impurity. And it turned out to be nickel nanoparticles.
Interesting. Well, great that you were so thorough in going through it, kind of realizing that little voice in the back of your head, something's not quite right here.
But it's too good to be true. It is.
Right. Well, Lee, great to hear about some of these challenges and how you guys work through them. But I don't want to just talk about the tough times in science. Can you tell us next about one of your successes, one of these exciting moments that you've had?
I think we've had so many of them, in a way. And also the problem with successful moments is you never really quite understand how good they were until you look back in time.
Right.
But one thing I'm really particularly proud of is when I work on an area of science called polyoxymetallase. We look at metal oxides, and they are very good at all sorts of things, from catalysis to electronics. And the problem with catalysis is there's a lot of competition. So I wanted to do something looking at water splitting and electrochemistry, and that would basically take some voltage from a battery and literally rip water apart and produce hydrogen and oxygen. And we looked into this, and I said to the postdoc, look, we've got to try and look for something that's not to do with catalysis, because that's too much competition and too many arguments, but let's look for a new phenomena. And what we found is we made a discovery where we discovered a completely new process for splitting water into hydrogen and oxygen. And what we were able to do by using this oxide, when you normally split water, you produce hydrogen and oxygen at the same time, and the hydrogen and oxygen can recombine together and explode potentially. And also, when you don't want to produce both the gases at once, you can't just turn one off. Well, in our system, we were able to produce oxygen easily first, and then whenever we need the hydrogen, we could produce it. Now, it's like one of my classic kind of people like, that's stupid. Why do you want to produce the gases at a different time? That's more effort, more energy. Okay, you do need to use a little bit more energy, but the nice thing is it's a bit like trickle charging a battery. When you've got pretty rubbish wind energy or some other renewable energy, you can just make oxygen all the time. And then when you've got enough accumulated, suddenly you need some hydrogen, you flick a switch and you produce hydrogen. And because in your system, the hydrogen and oxygen don't exist together, they don't break the membrane. So suddenly you have an electrolyzer that has much more durability and is much better. And if there's a failure in the membrane, it doesn't explode, so it's much safer. We make this breakthrough. I kept telling people, everyone said it's ridiculous. We couldn't publish. Then suddenly we got the paper published in Nature Chemistry, which I was very proud of, and to show this. And then we turned this two-step process where we needed two voltages, and we were able to discover that we could do it in two steps with just one voltage. So we could do all the hard work without producing any hydrogen. And whenever we needed the hydrogen, we just added a catalyst, and the hydrogen came out. And we published this paper in Science last year. And we're now basically starting a company to commercialize the technology to make a completely new type of gas generator.
Well, very, very cool. Congratulations on the success in science and on those publications. And so a lot of scientists are kind of getting to this point where they're finding that their technologies, the things that they're producing, the discoveries that they're making can have applications in the business, in the real world. So what is the process like for you now starting a company?
I'm an academic, and I think all academics are entrepreneurs. So I'm an academic entrepreneur. I get investment in my research and try and convert those into good papers, great trained people and new ideas. And I think I just wanted to do something new and ask an odd question. In this case, it was, could you use a metal oxide to soak up the protons and electrons before producing hydrogen? And then everyone looked at me as if I was like completely insane, but we did it and worked with it. And I think when we realized we had an advantage, we were then able to talk to the university's technology transfer people, and they put us in contact with a series of other people, and they came and listened to us and took the time. Because we made the effort to explain it to them, they got really excited. They could see there was a really interesting avenue to go down, and now we've exposed it. I'm trying to not be too possessive, but let the technology development take its own life. And what I was able to do, and I'm really proud of, and I'm really proud of my group, is I was able to headhunt really good scientists from industry who's come in, has made this their project, and it's going to be their company, really. And they're brilliant. They've got all the technology working, they're making the business plan, they're talking to investors. And so it's kind of sad. It's like watching a child, although I don't know about that yet because my children are too young to leave home, leaving home because you invented this science, or if you like, we made the discovery, you published the paper, and now you have to give it away.
Right. This is training for when your kids leave.
And who are better at doing it than you are. And I'm not a very good businessman. Well, you're not a very good scientist. But that's another problem for another day. So my job is not to do application-driven science. I hate the application coming first because I think scientists do themselves a disservice. But don't misunderstand. Don't hate application. What I love to do is be given money to be a bit crazy. And then, in return for being crazy, I think it's my duty, when I discover something I think could become a technology, to make sure the world gets the benefit. And that is the bargain I make with my funders, if you like, the taxpayer. Let me be a bit crazy, and I promise when I discover something really technologically useful that could help the world or whatever, or make a new company, I will do my best to make sure the right people come and use that.
I like it. I think that is a great approach, and wonderful to hear about your experience going through this. And we've chatted about your research going through the interview, and we've talked a little bit, just sort of touched on some of the opportunities you had to travel in your journey to getting where you are today. But I think this is a great opportunity that scientists get. And I'm curious to hear about you, Lee, and the places you've been. So can you tell us about one of your favorites?
My favourite places, I get to go to so many different places. I guess, well, I really enjoyed, I suppose, going to Japan when I started developing collaborations there, because I like hill climbing and there's some great places to go climbing in Hokkaido. But more than that, I just loved looking at all the gadgets and all the electronics and then trying to work out how to apply it. Some of the reasons I started 3D printing to robotics in the lab is because I got lost in Electric Town in Japan.
Oh, wow.
And found a robot that I was able to buy and program. Of course, I travelled there for the science. I learned an enormous amount from my Japanese colleagues, and we did some really fascinating work. But getting lost that day in that electric shop made me find these cheap robots. And for that was an unexpected spin-off. The other thing I like to do is go to meetings that have really odd... And this is where I started 3D printing, actually. And it was actually not so... Well, it's a lovely city. I went to London, and I got invited to the Bartlett, to an architecture conference.
Interesting.
And I went along because I'd been making some inorganic crystal gardens where the crystals grow into funny shapes and do cool stuff. And one of the guys there gave a talk on 3D printing, and I was like, oh, that's a bit boring and rubbish. You just print plastic stuff. I was like, but what if you could do chemistry in that? And then we got talking, and I managed to get him to come to my lab and run a workshop. So for me, I guess being in Japan and discovering the robots, and also going to the architecture conference in London and meeting this amazing 3D printer developer guy was great. And I think I would just say to people, I know you're busy and you've got to go to the right conference and you've got your exam mark and you've got the grants right, but occasionally reward yourself by going to that crazy conference you would feel that you have nothing to talk about with anyone there, and listen to what they're doing and just see what happens.
Absolutely. That's perhaps where some of your craziest ideas could come from. I like it. Really wonderful to hear about some of your travel experiences. And I think throughout our interview, we really hinted on the importance of the people that you work with in science. And I love chatting with scientists about the different groups they worked with over the course of their careers. And I think each group kind of has its own personality, which is often contrary to the way that scientists are typically portrayed in the media as very serious, very cold, isolated people. And I think in a lot of cases, that's not how scientists work on a daily basis. So can you share with us one of your own experiences, sort of the human side of science, one of these funny traditions or a memory that you've shared with your group?
Oh, there's so many. I mean, my group, they're known as the Cronies.
I like it.
When the group was getting bigger, the lab was getting more and more complicated. It was becoming quite obvious. It was quite hard to talk to me about mundane lab stuff. I thought I was being really progressive and so on, of setting up a mailing list called the Cronies that we would all communicate on. We'd get to know one another. So that became a bit of a tradition. But I realised that no one was using it. And I had an argument one day with one of my senior postdocs. He said to me, you don't know anything. You don't know anything. You don't even know that your group have a secret mailing list called Cronies minus Lee. That's how I know all the lab chatter. And so basically when someone has messed up the base bath or lost the solvents, or they have this secret mailing list where they don't bother me with all their little, let's say, negotiations to work it out. And I was both extremely annoyed because I'm a control freak and very proud of them for being independent and cutting me out of the equation.
That is awesome. Were you ever able to get them to respond to the main email chain that you were included on?
I think we have an unwritten rule, one of our traditions. Although I could go and read the Cronies minus Lee, I just don't.
Gotcha.
I don't act on it. If they email me, I will be in contact with them. We have our meetings as normal, but I never look at the mailing list to see who's grumpy with who or who's happy with who. I hope that they sometimes let me into the social stuff, because I don't socialise. I don't drink that much with the group. It's just something I just don't do, probably because I'm too old. But I like to have group social things like outings and so on, and because it's got a bit bigger, what we've done the last couple of years is I've tried to get enough consultancy money so I can hire a hotel and take my group away for a couple of days where we can just have a crazy brainstorm.
Well, that sounds fantastic. And I think I myself am also a control freak. So that's a pretty big step to kind of let that email list go without you. input and insight into it.
I am a control freak, but I really want to have smart people in my group. If you have people that just basically do what you say all the time, then it's going to be pretty boring pretty quickly. What you need is people to understand roughly where you're coming from and roughly where you're going and to challenge you. And oh my gosh, they challenge.
Well, wonderful to hear more about your group, Lee. It sounds like you've got a great environment there. And we've chatted a little bit throughout the interview about some of your work, but I want to talk about the big questions next. So, Lee, if we gave you everything, if things like funding and staff and technology and feasibility were not a problem, can you tell us about the one question that you would want to answer, the one project you would want to do?
Yeah, and I'm doing it. And it's not because I have enough funding, staff, technology, or feasibility. I'm doing it anyway.
Interesting.
I want to make a new life form and I want to understand where it came from. And I've broken it into feasible steps, PhD-able steps, fundable steps. This is probably why the UPSRC were quite happy about it and the university is quite happy, is that I basically was very successful and very successful. Touchwood will remain successful at writing grants, but who knows? The big picture that we're doing, the Origin of Life, is not funded by anyone. But are we just stealing their money and doing it? No, of course not. What I've done very carefully is I've built a matrix of projects that, when added together, sum up to this huge Big Bang genome question, if you like, in chemistry. And I just think life's too short. I realised a few years ago that I'm pretty good at, well, some of my other friends say I'm not, but I think I'm pretty good at explaining what I want to do and why it's interesting. Mm-hmm. And if I can then hook them together and convince a number of people, a number of funders, stakeholders, peers, that it's worth going for, why not go for it? And the question is, can we make life in a test tube in a few hours or a few years? And that's what we want to do. Now, even if someone came out of the blue and gave me as much money as I wanted, it's not funding, staff, or technology. It's time and expertise. So what I'm trying to do in my group over time is all the chemists that come in now, they have to learn a program. And I have to bring in robotics people that have to learn chemistry. And I have to bring in electrical engineers now that need to understand that circuit, if it isn't put in a box, if there's some ether there, it's going to catch fire.
Right.
I guess you haven't had an answer like this question before, but I really...
Yeah, I'm going to have to add some constraints to my list to give people time and expertise.
I mean, there's a very high chance, well, in fact, it's almost inconceivable that we're going to succeed. But if we just get even 1% of the way to understanding why we're failing, for me, that will be enough. And so at the end of my career, probably I might say, now I know how to do it. Can I have funding, staff, technology, and feasibility sorted out? And I would like to solve the research question because I truly would like to know where life came from. We spent more money on the origin of the universe and the origin of mass than we have the origin of life. And the problem with the origin of life is seen in a very historical context, and chemists are seen on their own working. I want to generate a massive collaborative framework. So I guess I can answer your question in a very verbose way. If you were to give me order of magnitude more funding than I have, staff, technology, I would build a huge collaborative experiment where I would make sure that chemists all around the world could get together like scientists of the LHC. We would basically build our origin of life collider, if you like, or maker.
I like it. Well, Lee, it has been phenomenal to get a look into your strategy in attacking this really big, almost seemingly impossible question on the origins of life. So fantastic answer there. And we've talked a little bit throughout our interview about some of the people who've helped you along the way. And I think you get some great advice from so many people along your journey as a scientist. I would love to end our show, Lee, with you giving us a piece of advice. So can you share maybe just one last piece of advice or pearl of wisdom?
Just make sure you're interested in what you're doing and don't give up. And I think the other thing is, if people take the time to give you criticism, act on it. I'm not just going, I'm going to make a life or dog off everyone. No, people are critical, and I try and address the criticism, say, but what about we do this experiment this way with these constraints, and we get this mechanistic data, or we get this observable out. And I think a lot of people hate criticism, and I tell you what, in science, the thing I would beg people to give me more of is honest criticism. Because honest criticism I can deal with. And I think if we can teach people to deal with their criticism, it's a much more honest way to go about doing profound things. It's no problem that half the community, more than half the community, think what we're doing is basically not going to work. But I'd like them to think that I'm not wasting money and people's time. And I think that to do that, we have to engage and listen to what their critique is. So I think having the ability to take criticism is something that you need to have. And I think I have, because I've had no choice.
Right. Well, very well said, Lee. I think that's a great point. And I know I myself, I'd much rather have someone tell me it's bad than tell me it's good when it's not. So fantastic advice there. Now, can you tell our listeners how they can reach out if they want to learn more about you and your work?
I think the easiest way is probably to go to my website, www.croninlab.com, or to email me, lee.cronin@glasgow.ac.uk, and I'll endeavour to answer emails. Sometimes there's a delay, but if someone's got a crazy question or inspired question, then I will do my best. I often spend a good proportion of my week discussing all sorts of things with all sorts of people, so why not?
Fantastic. Well, we appreciate that, Lee. And Lee, thank you so much for joining us today and sharing a piece of your story.
Thank you very much. Wonderful to be on.
It was a pleasure to chat with you. And thank you, listeners out there. We'll see you next time on another episode of People Behind the Science. Your voyage to the lives of today's exceptional scientists has just begun. You can find everything we talked about today, including our guests' favorite books, biographies, photos, and more, when you visit us at www.peoplebehindthescience.com. I look forward to seeing you next time on People Behind the Science.